Hello everyone, how are you? I hope that you are all good and doing well. In this video lecture, we'll be learning about the laser, and you know that I have already uploaded many videos based on the laser topics, and I have already covered some physics related to lasers like the Einstein coefficients, absorption and emission cross sections, light amplification, the threshold conditions, and the line broadening mechanism, in which I have broadly covered the natural broadening, collision broadening, Doppler broadening, etc. Those videos you can watch by clicking the I button on the right corner of the screen, and I will also provide the link of those videos in the description box, and you can watch those videos if you are interested. So let's start the video lecture. Myself Virendra Kumar, professor and scientist, and you are watching the Sai Academy YouTube channel. So friends, basically the light from both a laser and any ordinary source of light is electromagnetic in nature, but laser light can be extremely monochromatic, highly directional, and very intense. So, under this video lecture, we will be studying the various properties of the laser lights, laser beams. Light from the laser arises primarily from stimulated emission and the resonator cavity within which the amplifying medium is kept. And because of this, we gain the various properties of laser, such as directionality, spectral purity, high power laser, and extremely short pulse duration of the laser. In this video lecture, I will cover the directionality of the laser beams in detail. Friends, you know the light from a source of light such as a torch light diverges significantly as it propagates in the medium, but the beam coming from the laser system is in the form of a pencil of rays and seems to propagate without any divergence. But it doesn't mean that it has no any divergence or deviation from its original path. But the laser beam also diverges by a much smaller magnitude. The wave nature of light imparts an intrinsic divergence to the beam due to the phenomenon of diffraction. Thus, unlike a torch light where the divergence is due to the finite size of the filament, the divergence of the laser beam is limited by diffraction depending on the laser types, and this divergence can be very limited, up to the 10 to the power minus 7 radian or about 2 seconds of arc. This extremely small divergence leads to the many applications of the laser in the surveying, remote sensing, lidar, medical field, and industry. Here I have listed some special properties possessed by laser beams from different type of laser systems, like directionality. As I told, the divergence of the laser beams is very small, and the divergence is only because of the diffraction. Spectral purity. So the spectrum of the laser beam is highly monochromatic, and its spectral has a great purity, that is up to the 10 to the power minus 9 micrometer only. High power, it has the intense energy and ultra short pulses. It, because of the high power, it can produce the high electric fields. So under this, I will discuss directionality of the torchlight. You can see in this diagram that light is originated because of this filament, and since this filament has some dimension, therefore there is the chance of divergence from this much dimension of this filament. The filament can be considered to be made up of a number of point sources, and thus the light emanating from different points on the filament will travel along different directions. You can see here. So the light originating from every part of this filament will originate in the different directions, and thus the light emanating from different points on the filament will travel along different directions. So, after emanating from the different points of this filament, the light rays gets reflected from the parabolic mirror into different directions. So, if we place a convex lens in front of this torch light, and this lens is at a distance of focal length from the torchlight, they will not be parallel after getting refracted from the convex lens. They will travel in a different directions even after passing through the lens, and the exiting beam will diverge. So, if we consider the linear dimension of the if we consider the linear dimension of filament equals to 2 millimeter, and if the focal length of the convex lens placed before the torchlight is 10 centimeter, then we calculate the angular divergence given by theta is equal to arc by radius. Here arc is equal to the size of the filament, that is 2 mm, and radius is the focal length, that is 10 centimeter, which gives the value to 0.2 centimeter by 10 centimeter equals to 0.02 radian, which we can convert into degree as 180 by pi to 0.02 radian. This will give about 1 degree. Thus, we see that the angular divergence is approximately 1 degree. This divergence we can reduce, but then the amount of light will also get correspondingly reduced. While in case of the laser beam, the divergence is primarily due to the diffraction. Further, let us define the spot size to understand the divergence of the laser beam. So, spot size is nothing but the radius of the cross section of the laser beam. And for most of the laser beams, the spot size of the beam is about a few millimeters. So that means it is a very narrower. So here W naught is the spot size and theta is the angle of divergence. So let us calculate the angle of divergence if the laser beam has a free space wavelength lambda naught and a spot size W naught, then the angle of divergence can be given by theta nearly equals to lambda naught divided by pi W naught. So this is the formula for angle of divergence, and if we are talking about a typical spot size of 1 mm, that means if spot size is equal to 1 mm and wavelength, free space wavelength lambda naught is equal to 0.6 micrometer, then we can calculate the angle of divergence as theta is equal to lambda naught divided by pi W naught, that equals to 0.6 into 10 to the power minus 6 meter divided by 3.14 into 1 into 10 to the power minus 3 meter. So after simplification, we get that theta is equal to 0.19 into 10 to the power minus 3 radian. That is equal to theta is equal to 0.0109 degree. So we see that here if the this spot size is 1 mm, so angle of divergence is merely 0.01 degree. So that is very much very less in case of the laser beam. So this shows the directionality of the laser. Now a beam is said to be diffraction limited if it diverges only due to diffraction. And you know that in case of laser beams, the divergence is only diffraction limited. That means we can note that the laser beam from a laser diode has a significant divergence due to the small spot size of the beam. While in case of the laser, the divergence of the beam can be further reduced by simply using a lens in front of the laser diode, as there is no different point of emission as it was in case of the torch light. Friends, if you have not subscribed the Sai Academy channel till now, please subscribe it and press the notification bell so that whenever I upload the video lecture, you can get it. Now let us talk about the tight focusing of laser beam. Tight focusing means, because already we have discussed that divergence of the light laser beam is very less. So therefore, because of high directional properties of the laser beams, they can be focused to very small areas of few micrometer square. The limits to focusing are again determined by diffraction effects. Here, the smaller the wavelength, smaller the size of the focused spot. So, the focus spot depends on the wavelength. This property has been utilized in many applications of laser, such as in surgery, material processing, compact disc, etc. Now, when a convex lens images a point object, the size of the image point is directly proportional to the wavelength of the light waves, and also the ratio of focal length to the diameter. That means the size of the image depends on two things. Size of the image point depends on two things: wavelength of the light wave and ratio of the focal length to the diameter of convex lens used. That means we will now define a new quantity, the ratio of focal length to the diameter, and this ratio is known as f number. This parameter is used in specifying the quality of camera lenses. Thus, an f by 2 lens implies that the focal length to the diameter ratio is 2. That means if the focal length of this camera lens is 50 mm, then its diameter is equal to 25 mm. So f number is important for the quality of a camera lens. Smaller the f number for a given focal length, larger is the diameter of the lens. Smaller the wavelength, smaller the spot size, and similarly, smaller the f number, smaller the image size. Since an object can be considered to be made up of points, if we consider the imaging by the convex lens, the resolution provided by the lens will depend on the f number and the wavelength. For a given wavelength, for better resolution, we must have a small f number. So, if you are having a camera of small f number, then we will get better resolution for a given wavelength of light. So, smaller the f number of a camera, better will be the resolution of the camera. Now, when a laser beam is allowed to fall on a convex lens, then the radius of the focused spot is directly proportional to the wavelength and to the f number, provided the laser beam fills the entire area of the lens. If we take a lens having f number of 2, that is, if you are taking a lens having f number equals to 2, then this is f number. That is, the focal length is twice the diameter of the lens. Then we can calculate that for a laser beam having wavelength, free space wavelength, lambda equals to 600 nanometer, that is equal to 600 into 10 to the power minus 9 meter. The radius of the focused spot will be about radius of the focus spot will be about 1.5 micrometer. Thus, the area of the focus spot can be given by area of the focus spot can be given by pi w naught or omega naught square, and after calculation it comes out about 7 micrometer square. Now consider that laser beam has power of 1 megawatt, that is equal to 10 to the power 6 watt. Then the intensity can be given by dividing this power 10 to the power 6 watt to the by the area, that is 7 micrometer square. We get that the intensity will come out to be equal to 14 terawatt per centimeter square. Here we define that for a laser beam covering whole of the lens diameter, a truncated plane wave of the laser is incident on a lens without any aberration of focal length f. So this lens is assumed to have no aberration and it has a focal length f. Wave emerging from the lens will get focused to the spot of radius lambda f by a. So this single value is the radius, and total this gives the 2 lambda f by a. This is the estimated value. Thus we get for wavelength of lambda is equal to 600 nanometer and spot radius 1.5 micrometer and area of pi omega naught square, that is 7 micrometer square. We get that the intensity of the laser light will be so huge. Such intensity of light leads to the electric fields of 10 to the power 9 volt per meter. This 10 to the power 9 volt meter electric field is so huge that it can produce a spark in air. So in this figure, focusing of a 3 megawatt peak power pulsed ruby laser, the type of laser here is ruby laser. At the focus, the electric field strength are of the order of billion volts per meter. So in the experiment, it has shown that if we take a 3 megawatt peak power pulse Ruby laser and if you place a convex lens, then at the focus point, the electric field strength will be the order of billion volts per meter, which results in the creation of a spark in the air. Thus, it is important to note that we should use laser cautiously. Therefore, we show that laser beams, because of their high directionality, can be focused to extremely small regions, producing very high intensities and electric fields. Therefore, when the electric fields are very high inside a medium, the light beam can change the property of medium. Such effects are termed nonlinear effects. So we can conclude that when the laser beam of few megawatt is used and with the help of convex lens is focused to extremely small regions, they can produce a very high intensity and electric field, and because of this huge electric field they can change the properties of the medium, and such effects are known as non-linear effects. Now I will discuss that why we should not direct laser light into our eyes, because it can damage our eye even if the laser light power is of few milliwatt. So let us take, if the laser light beam of low power, suppose it is only 2 milliwatt, around 2 milliwatt diffraction limited laser beam, and it happens to fall on our eyes, then it get focused to a very small spot, and because of this it can produce an intensity of about 100 watt per centimeter square on the retina of our eyes. Therefore, this huge intensity of 100 watt per centimeter square can damage our eye, damage the retina. While if we take a bulb, 20-watt bulb, and we keep it a distance of about 5 meter from the eye produces an image of the bulb on the retina, and this would produce only an intensity of about 10 watt per meter square. So I would like to attract your attention that this is in centimeter square and this is in meter square. That is, this intensity is high because the area of spot is very small. It is in centimeter, and here area of spot is in meter. That means even a 20-watt bulb produces an intensity 10 watt per meter square, which is kept at 5 meter away from our eye, and therefore in comparison to this 20-watt bulb, 2 milliwatt laser power is harmful to our eyes. Therefore, because a laser beam can be focused to very narrow areas, it has found important application in areas like eye surgery and laser cutting also. Friends, it is generally asked that we should not look towards the sun because it has dual effects. It has huge energy density as well as having the ultraviolet light, which can damage our eyes. So let us see how much it is harmful to our eye and why. Friends, it is interesting to mention that when we are directly looking at the sun, the power density in the image formed is about 30 kilowatt per meter square. This is the power density of image formed in our eye if we look towards the sun. Let us calculate how it comes. Since we know that on the earth, about on earth, about 1.35 kilowatt power, this is power of solar energy is incident normally in 1 meter square area. Thus, the energy entering the eye is about 4 milliwatt. But since the sun subtends about 0.5 degree angle on the earth, the radius of the image of the sun on our retina is the radius of the image of the sun on our retina is about omega naught is equal to 10 to the power minus 2 into 10 to the power minus 4 meter. Therefore, area of image formed is pi omega naught square, that is pi into 2 into 10 to the power minus 4 square meter square, that gives 12.56 into 10 to the power minus 8 meter square. Therefore, power is calculated as 4 milliwatt energy incident on our eyes divided by the area of the image formed, which after simplification gives 0.3184 into 10 to the power 5 watt meter square. That can be written as 31.84 kilowatt per meter square. Thus, we see that if we directly looking at the sun, the power density in the image formed is about 31.84 kilowatt per meter square. Therefore, we should never look into the sun because the retina will be damaged not only because of the high intensities but also because of large ultraviolet content of the sunlight. So friends, we should avoid looking towards directly towards the sun because it has dual effect over our eyes. It has the huge intensities as well as the large ultraviolet content. Now see the application of the laser for creating the artificial stars in the sky. So friends, a very interesting application of the extreme directionality of laser beams is in the realization of artificial stars in the sky. So this is a center for creating the artificial stars by using the laser into the sky. At the height of about 95 kilometers above the surface of the Earth, there is a layer containing sodium atoms. If a laser beam at a wavelength of 589 nanometer is sent up towards the sky, then the sodium atoms absorb the radiation. These atoms absorb radiation of this wavelength and then get excited to a higher energy level. After absorbing this wavelength energy, the sodium atom gets excited into the higher energy level and then emit spontaneously when they get de-excited. So after going into the higher energy level, then they get de-excited and emit spontaneously. Some of this radiation is traveling towards the earth and then they resembles like a star. The position of this artificial star or guide star can be adjusted by changing the direction of the laser beam. So such type of stars are called guiding star or artificial star. Typically, pulsed lasers emitting a power of about 20 watt and pulse width of, this is the power used, and pulse width of the laser beam is used to be 100 nanosecond to create the star. This is the very interesting application of laser to create artificial stars in the sky, and such artificial stars or guiding stars have the great application in the correction of images formed by the telescopes on the earth. Friends, I discussed the directionality properties of the laser in this video lecture. I hope that you understood all these properties very well. If you have any doubts, please let me know in the comment box. I will be happy to guide you, help you. Thank you, friends, for being throughout all of the videos. Friends, if you have not subscribed the Sai Academy channel, please subscribe it, as I will upload the next video lecture based on the spectral purity, and it is very important topic related to the laser. So please subscribe the Sai Academy channel and be updated always.